Assalamu alaikum. In the last lecture, we learned that this set of three-phase coils placed 120 degrees apart from each other and supplied with three-phase currents. This will produce a rotating magnetic field B. This rotating magnetic field will be of uniform magnitude and it will be rotating with the same frequency as the frequency of the supplied voltage. The opposite is also true. That is, if we have a rotating magnetic field which is rotating with the frequency omega and is of uniform magnitude, then that rotating magnetic field will produce three-phase voltages in these rectangular coils placed at 120 degrees from each other. However, this is the situation when we have free space over here. In real machines, real AC machines, we do not have free space over here. Rather, we have a rotor of ferromagnetic material. And in today's lecture, we are going to derive an expression for induced voltage in real AC machines. We shall start with the simplest case. That is, we shall talk about a cylindrical rotor. Other shapes of rotor are also possible. For example, salient pole rotors, we can also have salient pole rotors. However, for the sake of simplicity, we shall talk about a cylindrical rotor. And instead of dealing with these coils, we shall only take one coil in this analysis, simple analysis. So on the stator, we have one coil. You can give any names to these sides of the coil. This is a rectangular coil with four sides. Let's name them in the same way as the book has used. This side is A, this segment is AB, this segment is BC, and then this segment is CD, and this front segment is AD. On this diagram, only this side can be shown by a circle, which is shown over here. Let's name them in the same way as that is there in the book. So this is side AB. This side CD is over here. Let's use the same name. This side is not visible in this diagram. That is at the back end of this diagram. And this front conductor is also not shown over here. Here we have a uniform air gap between the rotor and the stator, and we assume a sinusoidal distribution of the flux on the rotor. That is, the flux in the rotor that is given by B is equal to Bm cosine alpha. That is, at this particular angle, flux density is maximum, and as we move along this surface of this rotor, this flux density decreases. Maximum at this point, and at certain angle alpha, it is given by Bm cosine of alpha. That is, here if we have alpha, then flux density is has this shape. It decreases in this direction and also in this direction, and then again increases in opposite direction. Furthermore, what we assume is that this rotor is also rotating with certain frequency omega. So as a rotor rotates, flux density in the air gap will change. For example, it is at this time instant, it is maximum at this point, and after a certain time, this rotor would have been rotated. For example, after omega t equal to 90 degrees, rotor would have rotated to new location such that flux density will be maximum at this point. So flux density in the air gap is not only function of this angle alpha, but is also function of time. Therefore, as a function, if you write the expression for flux density in the air gap, that is given by V is equal to dm cosine of omega t minus alpha. For example, at omega t time equal to 0 and alpha equal to 0 depicted in this diagram, flux density in the air gap will be maximum at this point. It will be reducing a minimum at this, for example, in this air gap. At, for example, some later time instant, omega t equal to 90 degrees and alpha equal to the same angle, that is, we want to see the flux density in the air gap at this angle alpha equal to 0 at this time instant. So what will be the situation? 90 degree minus 0 is 90 degree, cosine of 90 degree is 0. So at this particular time instant, flux density here will be 0 and it will be maximum at alpha equal to 90 degrees. Alpha equal to 90 degrees is this angle. So at this particular time instant, flux density will be maximum here at this angle. And with this arrangement, we want to derive an expression for voltage induced in this rectangular coil placed over here. We know the relation for voltage induced. We know that a conductor moving in a magnetic field, voltage is induced in that conductor, and that voltage is given by V cross B dot L, where V is the velocity of conductor relative to the magnetic field, B is the flux density vector, and L is the length vector. So similar to our previous analysis, we shall take each segment of this coil separately. We start with this segment CD, which is easier to handle. Segment CD. So what is direction of linear velocity? In this case, in this expression, previously we were moving the conductor and the flux density was stationary. Here we have opposite situation. This flux density vector is moving and conductor is stationary. So flux density vector has this direction. This is direction of B. And what is velocity? This is velocity of the magnetic field. Linear velocity, direction of this is angular velocity is omega. Linear velocity of the magnetic field, that is in this direction. But this is the direction of movement of magnetic field. So what is velocity of this conductor relative to this magnetic field? The opposite direction. This is VAB, VCD. Is this point clear? Previously, we were keeping the flux density vector stationary and conductor was moving. Here we have opposite situation. Conductor is stationary and flux density vector is moving. Direction of linear velocity of this flux density vector is towards left. That is the direction of relative velocity of this conductor relative to the flux density vector, that is towards right. V is perpendicular to B, so V cross B is VB. And what is direction of V cross B? Rotate V in the direction of B. So V cross B is out of the surface of board, which is then parallel to this length vector. This length vector is placed like this one. So V cross B is parallel to length vector. V cross B is simply VB and dot L is VBL, and direction of this induced voltage is out of the surface of the board. What is B? B is given by this expression. We substitute it over here, and alpha corresponding to this conductor CD, that is equal to 0 degrees. So this alpha is 0 degrees. We have VBM L cosine of omega t. What is situation for this conductor BC? So EBC. Again, direction of V cross B, that is into the surface, V cross B, that is out of the surface of the board. This is out of the surface of the board. And what is this length vector? This is lying behind in this way, in this orientation. This BC is oriented in this way, connecting these two conductors. And V cross B is perpendicular to length vector. So V cross B is perpendicular to length vector, and therefore no voltage is induced in this segment BC, because direction of this vector V cross B, this is perpendicular to length vector, therefore their dot product is 0. The same is the case for this segment AD, and for AD no voltage is induced in this segment. Now we are left with this segment AB. So voltage induced in segment AB. What is that voltage? What is angle alpha corresponding to this conductor? This alpha is 180 degrees. Therefore, flux density vector is Bm cosine of omega t minus 180 degree. What is direction of this flux density vector? Upwards. So corresponding to this conductor, what is magnitude of flux density vector? That is corresponding to this conductor, B is equal to Bm cosine of omega t minus 180 degrees. Magnitude of this flux density vector here, and direction is upwards. What we can do is, for most of the students it is more convenient to visualize it in another way. This flux density vector with this magnitude is the same as this flux density vector. Let me draw it with blue marker. This flux density vector, that is in opposite direction but with negative sign. So both our situations are the same. This vector with this magnitude is the same as this vector with this magnitude. So since it is more convenient for many students, so let's have this situation. Then this is flux density vector, direction of flux density vector B. What is direction of its velocity? It is rotating in this direction. So this is velocity of the flux density vector. And what is direction of velocity of this conductor relative to this magnetic field? That must be opposite to this direction. That is, this is velocity of conductor AB and this is B. Hence, direction of induced voltage again can be determined by the right hand rule, that is out of the surface of the board. So therefore this voltage induced in this segment, that is V cross B. V is perpendicular to B, so V cross B is simply VB, and their cross product is parallel to L, so this is VBL, and B, if we substitute here this expression, then we have this negative sign over here. It means that the direction that we have assumed for this voltage, that is the out of surface of the board, actual polarity is opposite to that. Hence the total voltage that is induced in the coil is sum of all these voltages, and therefore E induced, that is equal to this voltage induced in this segment and then voltage induced in this segment. We also know that cosine of theta minus 180 degrees, that is equal to minus cosine of theta. That you can verify by expanding this trigonometric expression. That is cosine of theta minus this angle, that is equal to cosine of theta multiplied by cosine of this angle minus sine of theta into sine of this angle. So by that trigonometric relation you can verify it. Therefore, this cosine of omega t minus 180 degrees, that is equal to minus cosine of omega t. That negative sign cancelled out with this one, and this term added with this one. So we have VBML cosine omega t and plus this term also VBML cosine omega t. That is equal to 2 VBML cosine omega t. That is the expression for voltage induced in this coil. Let's rewrite it in a more convenient form. This linear velocity is related with this angular velocity by radius. We know that V is equal to R omega. R is the radius of this coil, this length. Therefore, E induced. So this is an expression for voltage induced in this rectangular coil in this particular arrangement. Let's rewrite it into another more appropriate form. For that purpose, what we observe is the total flux in the machine. So what is the total flux? We know that this is a cylindrical rotor and cylindrical stator. We have this situation, and here this is the flux density vector B, and its magnitude of flux density, that is distributed sinusoidally along the surface of this rotor and along the this air gap. So how much is total flux? We know that flux lines are entering from this semicircle, entering from this and leaving from this one. So to calculate the total flux, what we can do is, we know that flux is flux density multiplied by perpendicular area. So here is the situation. We have this cylindrical rotor and flux lines entering from here and leaving from here. So in this calculation, what area we should take? That is the area of this half circle, half cylinder, that is surface area of this cylinder, half cylinder. Why not full cylinder? Because the same flux lines which enter this perpendicular area, the same flux lines leave this cylindrical surface. So in calculation of total flux, we should take this area of this half cylinder. Furthermore, here situation is a little bit more complex. If flux density would have been uniform along this surface of the cylinder, then we could have used this expression. However, in this particular arrangement, we know that flux density is not constant. It is sinusoidally distributed along the surface of the cylinder. That is, B is equal to Bm cosine of alpha, where alpha is an angle, this angle measured from this position. So what to do now? In this particular case, if flux density is not uniform along the surface of this cylinder, then flux has to be computed by this relation, B multiplied by differential area and then integrated. That is, to calculate the flux density, we divide this whole cylindrical surface into small strips, very small strips. strips of length equal to length of cylinder, and this differential length, the differential so this area of this strip is dA multiplied by flux density in this area, and here in this small area we can assume that in this small differential area this remains constant, so B multiplied by differential area and then integrate it, where B is equal to dm cosine alpha. Now what is this differential area? Differential area that is this area, this small area of this surface of the cylinder shown over here is equal to this length, which is equal to length of the cylinder, and multiplied by this small length of breadth of this strip, that is, this is dm cosine alpha multiplied by L into ds. ds is this small differential length. How this length is related with the radius of this coil? We know that S is equal to r theta. Therefore, r in this particular case angle is denoted by alpha. So r alpha, that is ds, is equal to r d alpha, and hence we have this situation bm cosine alpha L r d alpha. And what should be limits of integration? We are going to integrate it over the half cylinder, that is from alpha equal to minus pi by 2 to alpha equal to pi by 2. That is limit of integration is from minus pi by 2, alpha equal to minus pi by 2 to pi by 2. And you can easily evaluate this integral. Integral of cosine alpha is sine alpha. So we have sine of pi by 2 is 1 and sine of minus pi by 2 is minus 1. So this comes out to be equal to 2, and hence this is 2 bm L r. Hence flux, total flux in the machine, that is given by this relation 2 r L and dm, that is equal to the total flux in the machine. So we replace that total flux into the expression over here and we get this relation. Over here we have assumed single turn of the coil. If there are multiple turns, then how much voltage will be induced in the coil? In that case, voltage induced in the coil, that will be equal to. So this is the expression for voltage induced in this coil when we will have NC turns on this coil. In this derivation, we have assumed this angle as angle 0. However, if we take this angle as 0 angle, then instead of this cosine, we shall get a sine wave, NC phi omega sine omega t. If this angle is taken as the reference angle, 0 angle, then voltage induced in this coil will be given by this expression. So what if we place another coil over here, that is a coil with an angle of 120 degrees from this coil. So that is, if we have this stator with one coil over here, let's again give them the same names which we used previously, and then place another coil at 120 degrees from it. Let's call it coil B dash, and with the same rotor with sinusoidal flux distribution. Then what will be voltage induced in this coil? The voltage induced in this coil will lag the voltage induced in this coil by 120 degrees. That is, voltage induced in coil VB dash, that will be equal to, and if we have another third coil which is another 120 degrees from this coil, then voltage induced in this coil ECC dash will be equal to, so this is voltage induced in the first coil. That is, if we have this machine, this arrangement with 3 coils with placed 120 degrees apart from each other, and a rotor with sinusoidal flux distribution, and the rotor rotating with frequency omega, then 3-phase voltages will be induced in these coils. If you wish, you can also write these voltages in, this is the peak value of the sinusoidal signal if you want to determine the RMS value. So RMS value, that is equal to the peak value divided by square root of 2. So NC phi omega divided by square root of 2, where omega is the speed of the rotation of this rotor. Generally, you remember that we are more convenient, this omega is in radians per second, and we are more convenient with the revolutions per second or cycles per second. So if we write the same expressions in cycles per second, so we have NC square root of 2 phi multiplied by omega. Omega is 2 multiplied by the frequency, which is in cycles per second. Therefore, that is equal to square root of 2, this 2 and this is square root of 2. That is the RMS value of voltage induced in these 3-phase coils. In the next lecture, we shall derive an expression for induced torque in this real AC machine.